Yes, so welcome back to the part four of the video that I'm making on brain analysis on that series. In my first video, I discussed summation by parts, and the part two of the video, I discussed absolute convergence, and the part three, I discussed the algebra of um, series, where I put more emphasis on the product uh, which is called Cauchy product. In this video, I'm going to be talking about rearrangement. So I discussed summation by part theorems and I proved it in my previous videos. I discussed the Richlet test and I proved it in my previous videos. Also, I talked about absolute convergence, the definition, and I proved the theorem under that as well. Cauchy product, and I proved the theorem as well. I also gave an example to show that uh, the product of two convergent series is not necessarily convergent. If neither of those series converges absolutely. I gave these examples well laid out to show that that is the case. Now in this video, I'm going to be talking about rearrangement of a series. It's very interesting to know that when you rearrange the terms in the series, you could be getting different information. So let kappa be a function from n to n, natural number to natural number, be a bijection, given a series, a sum of an, the series ak kappa of n is called the rearrangement of an. So imagining you have a series and you have a naught plus a1 plus a2 plus a3 and you decide to rearrange the terms. That's what rearrangement means. So I can decide, for example, to pull all the terms, the all terms. I can pull them together and I can start maybe instead of having A1, A0, A2, A3, A4, A5, A6, I could just decide to have A2, A1, A3, A4, sorry, A2, A1, A4, A3, A6, A5 in that way. And somebody will ask, so is it not the same series? So does it matter whether I move things around or not? That's what is interesting. So let's look at this remark. If the sum of an converges but not absolutely, then some rearrangement may convert to different sum. This is how powerful absolute convergence of a series is. Sometimes you wonder, okay, if a series already converges, so why do I need it to converge absolutely? This is one of the very, very important reasons. If the series does not converge absolutely, when I rearrange the terms, some rearrangements may convert to different sum. It means that if I have a series an and I rearrange it in one form and I look for the convergence, it could convert to a number. When I rearrange it all over in different ways, it could convert to another number. That's not all. Some rearrangement may even diverge, may not converge at all. The original series may even converge. But by the time you rearrange things, you may not even get some of the rearrangements you get may not even converge at all. This is a very deep phenomenon, and understand that we are dealing with infinite series, infinite sum. All right, so Riemann came up with some theorem. So if I let the series given by an be series of real numbers which converge, but not absolutely convergent, right? Suppose I have alpha and beta finite this way, where alpha is less or equal to beta, then there exists a rearrangement sum of an prime whose partial sum Sn prime satisfy the lim-inf of Sn prime is alpha and the lim-sup of Sn prime is beta. Now this is the main theorem. If the series an is a series of if sum of an is a series of complex numbers that converges absolutely, the word absolutely is a key. Then every rearrangement of this series converges, and all rearrangement converge to the same sum. So when a series converges absolutely, it does not matter how I rearrange the terms. Every rearrangement you can get from that series will converge, and will not only converge, they all will converge to the same sum. This is a very powerful theorem, and it's a deep understanding that every student should be aware of. So this follows from comparison of partial sums using absolute convergence of this. I'm not going to be proving this, but this is a very, very serious and important concept that I would like all the students to take very note of. I'm going to stop here, and in my next video, which is the part 5, I'm going to be going into examples. I'm going to be taking on some examples to actually show how to show that a series converges absolutely. I will see you in my next example. Thank you very much.